Okay, welcome back. So we've talked about addition rules. We've talked about what it means to be mutually and not mutually exclusive. When to add probabilities and when to add and then having to subtract any overlap. Well, if we can add, we can also multiply. So we have these multiplication rules that will help us to find things that occur in a sequence. So now we're having more than one probability happening. We have two different times. We have independent and dependent. We say that two events are independent if A occurs and does not affect B. So we have an independent if A does not affect B, right? They're independent of each other. They don't change the outcome of either one. And then the opposite of that is, well, dependent. So we have this idea of dependent events, and that means if the second event, if the first event affects the outcome of the second. So if A does in fact affect B. So we have some examples here about independent and dependent happening. So when we're talking about multiplication, these are things having to do with and the probability of something and the probability of something else. We want to determine if they're independent or dependent. So for A, tossing a coin and drawing a card from a deck. Do those two things have anything to do with each other? If I toss a coin, right, does that have any effect on the probability of me picking a card from a deck? I hope you're thinking that the answer is no. So we would say those are independent. They don't affect each other. A coin and a card don't really have much to do with each other. Now let's go to B. So drawing a ball from a box, not replacing it. So if I don't put it back and taking out a second ball. Okay, let's think about that. If I have a ball in a box, right? Here's my box. Let's say I have 6 balls in there. If I take one of those balls out and I don't put it back, I did not put it back, how many do I have left? I only have 5 balls left. So if I go to pick another ball, did I change the probability? Yeah, I changed it because first time this was a probability out of 6. Now I've changed it and my probability is now only out of 5. So this now is dependent. It's a dependent. These are dependent events. They totally affect each other. Oops. Wrong C. Alright, what about getting a raise in salary and purchasing a new car? Are those independent or dependent events? Well, if I get a raise, I have more money. And if I have more money, then I can buy a better car. So I would say that those are definitely dependent. The kind of car I buy definitely depends on how much money I make. Alright, what about driving on ice and having an accident? Are those two related events? If I drive around on ice, will I maybe get into an accident? Maybe, maybe not, but most likely I could. It could happen, and since it could happen, then these are dependent events. Alright? Having a large shoe size and having a high IQ. Now, despite what some of you may think, just because you have big feet does not mean you have a big IQ. They're not related. It might be funny to joke about and talk about, but those are not related things. So we say these are independent events. They have nothing to do with each other. What about smoking and having lung cancer? There's some debate on that, but I think most studies have shown pretty conclusively now that the more you smoke, the higher your chances to having lung cancer. And so say it's not true for everyone, but it's true for quite a few. I would go ahead and say for argument that this is a dependent event, that they are related and they can affect each other. All right, eating an excessive amount of ice cream and drinking an excessive amount of Coke. Can I drink a whole lot of Coke and not eat a lot of ice cream? And can I eat a lot of ice cream and not drink a lot of Coke? They might taste good together, but really these are independent events. One is drinking, one is eating. I might do them at the same time, but normally this is actually an independent event. Okay? They're only dependent if the chances of one happening will affect the other one of happening. So whether or not I eat a lot of ice cream doesn't really have any effect on if I drink a lot of Coke. And just don't argue. Let's just going to say that they're independent. So we come to multiplication rule number 1. So if two events are independent, then we say that the probability of A and B happening, remember that keyword and, we say the probability of A times, because we're multiplying, the probability of B. That's pretty much it. So we have the probability that a coin is flipped and a die is rolled. Remember, we have a 6-sided die. Find the probability of getting a head on the coin and a 4 on the dice. All right, so when we toss a coin, there's two sides. There's heads and there's tails. So there's only two outcomes. When we roll a die, there's 1, 2, 3, 4, 5, or 6. Those are all the options. So there's 6 total outcomes. I'm just trying to point that out. Make sure we remember. So we're looking for the probability that we flip a coin and get heads, and then roll a die and get the number 4. So the probability that we toss and get heads times, that's and, probability that we get roll a 4. Well, what's the probability that you pick heads? 1 out of 2. There's only 2 outcomes, heads or tails. Times, how many times can I get a 4? I can only get a 4 once out of a total outcomes of 6. And if you don't remember, when you multiply fractions, you multiply straight across. So 1 times 1 is 1 on top. 2 times 6 is 12 on the bottom. So you have a 1 in 12 chance, a 1 in 12 probability of flipping a coin and getting heads and rolling a die and getting 4. Okay, what about a card being drawn from a deck and replaced? So we're putting it back. So since we put it back, it doesn't change our total outcome for the next thing. So that's good. That's the key here. And replaced. Key word. Underline it. Then we draw a second card. So find the probability of picking a queen and then an ace. So probability of a queen and an ace. And since we put it back, we can keep going. So the probability of a queen times the probability of an ace. Well, there are 4 queens in a deck out of a total of 52 cards. And there's 4 aces in a deck out of 52 cards. So we can simplify 4 over 52 is 113 times 113. And when we multiply that across, it's going to give us 1 over 169. So notice that's a pretty small chance that we pick a queen and an ace in order. Alright, so we have an urn, which is kind of like a jar or a jug. Or a box, if you want to say. It has some marbles in it. So in our urn, there's my urn, I have 3 red marbles, I have 2 green marbles, and I have 5 white marbles. So how many marbles do I have total? I have 10 total marbles. I always like to draw a picture or like tally things up on the outside. Okay, so we're taking it out and it goes, and it's replaced. So remember that keyword there, replaced. Important. A second marble is selected in its color. So find the probability that we, A, pick 2 green marbles. So 2 green. So the probability that the first one is green times the probability that the second one is green. Well, how many chances do we have being green the first time? We have 2 out of 10. And if I put it back, then I still have the same chance again to picking a green one a second time. So we get 2 out of 10 over 2 out of 10, which is 2 times 2 is 4. 10 times 10 is 100. And this will simplify to 1 over 25. That was A. All right, let's see B. Probability of selecting 1 green and 1 white marble. So the probability that I get a green times the probability that I get a white. So let's see. For a green marble, I already know that's 2 out of 10. Times the probability of getting a white marble, there's 5 whites out of 10. And again, we can multiply. This is going to give me 10 out of 100, which simplifies to 1/10. Alright, let's see. The probability this time of picking a 1 red marble and 1 green marble. So the probability that I pick a red times the probability that I pick a green. So how many red? We have 3 out of 10 red marbles times 2 out of 10 green marbles. This is going to give me 6 out of 100, which will simplify to 3 over 50. All right, this next question is a little bit different, number 4. So we have a survey that says that there is a 40% chance. That's what that means. 40%, which also can be written as 0.40. That's how we're going to write things properly. That suffer from stress at least once a week. So this is just in general. If we pick 3 people at random, find the probability that all 3 of them say they will suffer stress. So we're talking about a repeated probability here. So the chances or the probability of picking a person is the same every single time, but I need to pick 3 of them. So each person has the same chance as the one before. It doesn't change. So the probability that all 3 people are stressed out is the probability of picking the first person times the probability of picking the second person times the probability of picking the third person. And I said each person has the same exact chance. So the first person has a 40% chance. The second person also has a 40% chance of getting picked. And the third person has a 40% chance of getting picked. So really this ends up being 0.4 cubed because we picked 3 people. And then this is going to give us 0.064 chance, or a 6.4% chance that we pick 3 people out of randomness that have stress. All right, now we have multiplication rule 2, and this one is called a conditional probability. And you can think about it as, you know, your parents say you have to do something, or you're allowed to go do this if you go do all these other things first. There's conditions placed on it, right? So this means this is a dependent event. So we're talking about events that affect each other, right? Like if you do all your homework, then you can stay up late. Or if you do all your chores, you can have some extra money. And in order to get the extra money, you have to do the chores. So they're dependent on one another. Okay? So when we're talking about these dependent events, we're still talking about A and B. So we're still multiplying here. But it's now the probability of A times the probability of B given whatever happened in A. And I'll tell you what that means. So the example we have here is a person owns a collection of 30 albums or 30 CDs. They used to be called albums a long time ago. 30 albums, of which 5 are country. So 30 albums. 5 are country. If we pick 2 albums at random and we don't put them back, so if I don't put them back, it's going to change the total number of albums I can choose from. What is the probability that both of them are country? So you have the probability that the first one is country, and that one has a total of 30 choices, times the probability that the second one is country, given you picked the first country one. So now since I picked one and I don't put it back, now my total has changed from 30 to 29. So my first choice is 5 out of 30. And then this time it's 4, because I picked one of the country albums, so it's gone, which changes the total number to 29. And when you work this out and simplify it, we get 2 out of 87. Alright, so let's talk about probability in a deck of cards. This might help you see the idea that if we pick something and we don't put it back, that not replace, it's changing the total number of things I have to choose from. So if I was trying to pick, so these are 52 cards altogether. So the probability of picking a jack, right? So here are my jacks. Okay, these are my jacks. And if I pick one of them, right? So one of them is now gone. I picked him. That was the one I picked at random. I no longer have 52 cards. Now I only have 51 cards to choose from. And now I no longer have, for the first one, right? I had a 4 out of 52 chance. Then I picked him and he's gone. He's picked, he's gone, he's no longer in the deck. I now only have 51 cards and how many jacks left to choose from. So the probability of the second jack, I only have 3 I can choose out of a total of 51. That's what makes this dependent. By not putting it back, I'm changing the total number of cards. and I'm at the same time changing how many jacks I have to choose from. So this is that idea here. So if we're talking about the probability of getting 2 jacks and I don't put them back, I have that probability of picking the first jack times the probability of picking the second jack, given that I already picked the first one. So we already did it. So we had the first time we have a chance of 4 out of 52. But since I picked him and I didn't put him back in the deck, that changed my total number of jacks to 3 and the total number of cards to 51. And then you can multiply that out and simplify it. And this would give me 1 over 221. Let's see another one. So the probability of picking an ace and then a king. So I need to find the probability that I pick an ace times the probability that I pick a king, given I've taken an ace away. Well, how many aces are in a deck? Well, there's 4 aces out of 52. And so since I picked one out, I took him away, I only have 51 cards left. But how many kings do I have? I still have 4 kings. I didn't change the number of kings, but I did change the number of total cards I had. So keep that also in mind. So this is going to give me a number that simplifies to 4 over 663. Right? C. Probability of getting a club and a heart. So probability of getting a and a heart in order. So probability of a heart, then a club, because I want to get them in order, heart then club. So the probability of a heart times the probability that I pick a club after I pick a heart. So how many hearts are in a deck? There are 13 out of 52 hearts. Then if I pick one of those, does that change the number of clubs I still have? No, I still have 13 clubs, but it changes the total number I have, which is 51. Multiply that out and simplify, and we get 13 over 204, I believe. Alright, and our last one. What's the probability of getting 2 clubs in a row? So I got a probability of picking my first club times the probability of picking a club, not putting it back, and picking another club. So there are 13 out of 52 clubs. Now this time if I take a club out, that gives me 1 less club to choose from, and it also gives me 1 less total to choose from. Kind of like my jacks, how that one worked in the beginning. And then I can work this out and simplify it, and this should simplify to 1 over 17. Okay, we're talking about number 3. So here's the situation. We have 2 different boxes that have 2 different amounts of marbles in there, and we have a coin that we're going to toss. And the stipulation is if it falls on the heads, then we're going to pick box 1. And if it falls on tails, then we're going to pick box 2. So we have, let's do heads. Heads, then we pick from box 1. Right? And box 1 has 2 red marbles and 1 white. If we flip a coin and we get tails, then that means we have to choose from box 2. And in box 2, we have 3 white marbles and 1 red. So we're looking for these different combinations now. So we want to find the probability of getting a red marble. Probability of getting a red marble. Well, there's 2 different situations. There's probability of getting a red marble if we flip heads, because there's reds in both boxes. Or, oh no, or means add. The probability that we get tails and we have to get box 2. So now we're kind of combining multiplication and this addition idea. So the probability that we land on heads is what? 1/2, right? 50% chance. Times, so if we're on heads, that means we're in box number 1. Well, how many red marbles are in box number 1? 2 out of 3 total, right? So that's the 1 set. Or we're adding probability that we get tails. Well, that's also a 50-50, 1/2 chance. And we get, that means we have to pick this time out of box 2. And how many red marbles are in box 2? We have 1 out of 4 total. So we have 1/2 times 2/3, which is going to give us 2/6, plus 1/2 times 1/4, which is going to give us 1/8. And when we add those two together, and we have to get like denominators, and if you have a fancy calculator that will do fractions for you, 2/6 plus 1/8, and you can put it in correctly, you will get 11/24. That's our probability of picking a red marble. Alright, so we still have this idea with heads and tails. And this next one says, find the probability of selecting a white marble. Well, let's think back to complements. Remember complements? That means the probability of picking a white marble plus the probability of picking a red marble, regardless if we get heads or tails, regardless if we do box 1 or box 2, if I add them together, it has to equal 1. You with me? That's a 100% chance that I pick a white or a red. So the complement, remember the complement? The complement, or the opposite of picking a red marble, would be picking a white marble. That would be the complement of red. That means that the probability of picking a white marble, regardless of which box I get it from, is 1 minus the probability that I just figured out about picking a red. Well, we just figured that out, didn't we? It was 11/24. So 1 minus 11/24 is going to give me 13/24. And there's no need for me to figure it all out again. What's the probability of picking heads times the probability of picking a white this time, plus the probability of getting a tails, and doing all that. It's the direct opposite, because there was only 2 marble choices in the boxes. So I can use the complement. See how much easier that makes that if we use the complement? Alright, so the last part of conditional probability, if we rearrange some things, we actually get to find the given piece, that piece that was changing. So we have the probability of B given A is equal to the probability of A and B divided by the probability of just A. So we have this and on top divided by the probability of the bottom. It's really not as complicated as it seems. So we have this box that contains black chips and white chips, right? A person selects 2 chips without replacement, so he doesn't put them back. So that's where it's changing it. They're dependent now. If the probability of selecting a black chip and a white chip is 15/56, there's the and, the probability of both is 15 over 56. And the probability of selecting a black chip on the first draw is 3 over 8. So the probability of getting a black chip is 3 over 8. Find the probability of selecting a white chip on the second draw given, so this is the given one we're looking for. The first chip was black, so we're actually looking for that given. So white, given that it was black, is equal to the probability of the and divided by the probability of the black. Well, the and probability was 15 over 56. And the probability of choosing the black was 3 over 8. Now, you're going to have to either know how to divide a fraction by a fraction or how to input this into the calculator correctly. And hopefully when we do that and simplify, we will be getting 5 over 7. So you're looking for the and then you're looking for the second half. So the second half goes here, the and goes on top. Let's look at the second one. So the probability that Sam parks in a no parking zone and gets a ticket is 0.06. There was that keyword, the and. The and probability was 0.06. The probability that Sam cannot find a legal parking space and has to park in a no parking zone is 20%. So the no park is 20%. What's the probability on Tuesday Sam arrives at school and has to park in a no parking zone? Find the probability that he will get a parking ticket. So the probability that he gets a ticket if he parks in the no parking is the probability of both of those things together, the and, over the probability that he is in the no park zone. Well, the probability that the and together is the 0.06 over the probability of no parking is 0.2. And using your handy dandy calculator, you should get 0.30. So that should help you do all of probability practice 2.